So my name is Jon Hollinger. I'm a fourth-year PhD student in the Affairs group at the University of Toronto in the chemistry department. And what our focus, or it mainly is in the group, is conjugated polymers for photovoltaic applications. And in that vein, my main research objectives are to look at addressing a couple of the main problems and challenges with current materials. And polythiophene is one of the most studied polymers in this field, and it has a couple of issues. First of all, it doesn't absorb as into the red wavelengths as would be optimal. And since morphology is so important in a bulk heterojunction cell, which is the kind that we fabricate, we wanted to look at making a block copolymer with one block of polythiophene and one block of polyselenophene, which is the selenium substituted analog of polythiophene. Now, in a couple of initial studies that we did, we found that although these heterocycles are structurally analogous, the polyselenophene was known previously to absorb more into the red wavelengths because the band gap is narrowed. And you can see that just with the simple thin film UV trace. The polythiophene is here in blue and the polyselenophene is in red. And if you make a block copolymer, you see that the absorption onset is matched with the polyselenophene homopolymer, indicating that the band gap is maintained from the pure selenophene phase. What was interesting to us was that we saw this vibronic fine structure in the form of a shoulder in the red wavelengths, which is in the homopolymer indicative of pi-pi stacking interactions. And what this suggested to us was that these polymers phase separated in the solid state, which is interesting because these phase separations happen on size scales that line up nicely with the exciton diffusion lengths of these cells. So this could not only optimize the absorption profile, but possibly also the morphology in order to increase the overall efficiency of these devices. So when we were looking at the block copolymer devices, and I have to give credit to Dong Gao in our group for fabricating these devices and testing them, we found that actually a couple of interesting things. First of all, the block copolymer of poly-3-hexyl-thiophene, poly-3-hexyl-selenophene did harvest more red photons than the poly-3-hexyl-thiophene homopolymer. And interestingly, we found too that these nanostructures that they were forming when blended with C60 derivative electron acceptor PCBM seem to form more thermodynamically stable structures. So there wasn't the same decrease in decrease in performance with annealing temperature as we saw with the P3HT homopolymer. So you can see the block copolymer maintains a relatively high performance as the annealing temperature increases, whereas the P3HT drops off pretty drastically above 75 degrees. And the long-term stability was also something that we investigated, and we found that once we fabricated the device and annealed it at 80 degrees after fabrication, we found that it seemed like these structures formed by the block copolymer with the PCBM acceptor, that morphology was more stable than it was with either P3HT homopolymer or just a physical blend of poly-3-hexyl-selenophene and poly-3-hexyl-thiophene homopolymer just blended together. So again, this the relative decrease in device performance with this post-annealing step affects the block copolymer much less. So it says that these structures are more stable overall. Another avenue that we've investigated is generating statistical copolymers. So polymers where selenophene and thiophene units are distributed randomly along the backbone instead of two distinct blocks. And what we found in this case is that we still have the overall reddening of the absorption profile, as you can see with the statistical absorption profile in thin film is here in the middle. So we still have that overall reddening of the absorption compared to P3HT. And we still have, despite this random distribution of monomers along the chain, a semi-crystalline nature, which is really important to have that pi-pi stacking in order to facilitate charge transport. But the statistical nature of the polymer does make it much more soluble and thus a lot easier to work with. The block copolymer, polythiophene, isn't the most soluble polymer in the world, and polyselenophene is actually worse. So these polymers are not the easiest to work with. The statistical copolymer is it really makes the device fabrication process a lot easier to do, while still maintaining the relative redshift in the absorption profile. So this is the kind of the work that we've been doing, and it's work that we're continuing to look at. We want to look further at making unique structures with block copolymer in an attempt to get better morphologies that will work better in the bulk heterojunctions to facilitate charge transport and maintain that broadened absorption profile.
Now between the valence and conduction bands, you've got a forbidden gap. And if the gap you've got is just too wide, you'll lose your photons in a snap. Now if the gap you've got is far too narrow, you'll catch the whole darn fleet. But that won't do you any good, 'cause all you'll get is heat. Oh, solar energy, yes, solar energy. We can have our fun with the power from the sun using good old PV.